Today we will be discussing Dantzig's simplex algorithm. The simplex algorithm is used to solve linear programs. A linear program is taken as input and an optimal solution is produced. If you are at all familiar with Gaussian elimination, then the simplex algorithm may be somewhat easier to understand, as the two have some similarities. We begin by giving you a general overview of what the algorithm does and what it achieves. The algorithm takes some linear program as input. The program is first converted into a form that the algorithm could understand. It then iterates over the input and performs some computation given a certain condition is met. After this, a solution is computed based on both the original linear program and the results of the previous computations. Said solution is then returned in the form of an n vector that is an optimal solution to the linear program taken as input. We will now explore the algorithm in more depth. On screen now is a general way of expressing a linear function in standard form, with important terminology underlined in blue. A linear function is not in standard form if 1. The objective function is a minimization rather than a maximization. 2. There are variables without non-negativity constraints. 3. There exist equality constraints, or there are inequality constraints with opposite signs. From now on, we will assume that the linear program we are given as input is already in standard form. Before we continue, we'll be introducing the terminology used to describe solutions to linear programs. A setting of the variables x in the initial objective function that satisfies all the constraints is a feasible solution. A setting of the variables x in the initial objective function that does not satisfy at least one of the constraints is an infeasible solution. If you set the variables in the objective function to those in the solution, we get the objective value. The maximum objective value of a feasible solution over all feasible solutions we call the optimal solution, whose objective value is known as the optimal objective value. If there are no feasible solutions to a linear program, then that linear program is infeasible. Otherwise, it's feasible. If the program does indeed have some feasible solutions, yet does not have a finite optimal objective value, we say the linear program is unbounded. Now we shall take a look at slack form. We do the conversion from standard form to slack form for efficiency purposes. The idea is simple. Deduct the left-hand side from the right-hand side and equate the resulting expression to a new slack variable. They're called slack variables because they measure the difference or slack between the left-hand and the right-hand sides of the equation. What we have done is turn all of our inequality constraints into equality constraints, with the exception of the non-negativity constraints. Finally, we use variable z to denote the value of the objective function. We'll be denoting our slack variables as they appear in the blue box. There's a little bit more terminology though. Variables on the left-hand side of the equalities, those underlined in red, are known as basic variables, whereas those on the right, underlined in green, are non-basic variables. So now we have our linear program in its slack form. We can find a feasible solution by setting all non-basic variables to 0. Should the non-negativity constraint hold for all our basic variables, we have ourselves a basic feasible solution. We'll now begin iteration. First, a non-basic variable with a positive coefficient is chosen from the objective function. The reason for this is we want to increase the objective function by increasing our chosen variable's value. This variable will be known as the entering variable, as it will be entering one of our equality constraints. It will be easier to understand this process given an example.
Let's go through an example. We convert the example into slack form as shown on screen. Here we have set out the problem in a tableau to make calculation easier. For the first iteration, we must select a pivot column, which will be the column with the most negative number in the bottom row. To choose the pivot row, we divide the values in the last column by their corresponding value in the pivot column, and choose the one which is the smallest positive value. Here we see that the pivot is 5 in the x2 column. The next step is to divide the entire of the pivot row by the pivot value. Then, for all other rows, you subtract or add a multiple of the pivot row, such that all the values in the pivot column are equal to 0. This completes the first iteration. For the second iteration, we do the same again. this time selecting 16 over 5 in the x1 column. Again, we divide the pivot row by the pivot value. Then we add or subtract a multiple of the pivot row such that all values in x1 are 0, other than the pivot row. Now that there are no more negative values in the bottom row, we have reached an optimal solution, which is calculated as shown.
And that is how the simplex algorithm works. Almost. You see, the simplex algorithm makes the assumption that the initial solution is feasible, and this may not always be the case. We may have a variable that breaks the non-negativity constraint upon being initially converted to slack form. The initialize simplex function in line 1 here not only converts the linear program into slack form, but it can also convert it into a slack form wherein the basic solution would be feasible. This is done by changing the linear program to an auxiliary linear program. We know L is feasible if and only if the optimal objective value of L-aux is 0. We can do this simply by solving the auxiliary program as normal through pivoting until we get a feasible solution to both L and L-aux, with the latter objective function equal to 0. Should we find that there is no feasible solution to the auxiliary program, initialize simplex simply returns infeasible, and the simplex algorithm terminates. We know the simplex algorithm works by the fundamental theorem of linear programming. The simplex algorithm is not a polynomial time algorithm, though there are particular inputs that exist which run incredibly slow due to the number of iterations it incurs. However, the simplex algorithm is very efficient in practice.